Alright, this is the last video in which I'm going to be talking about this function f of x is x squared times 3 minus x. We asked about increasing and decreasing in the previous video, absolute extremes in the first video. We'll now take a look at where's f concave up and down and all the inflection points. So we're looking at this f of x. Since we're talking about concavity, that's going to be about the second derivative. So let's just crank through here to get those other derivatives. There's my f of x. F prime of x is 6x minus 3x squared. My f prime of x, 6x minus 6 minus 6x. I wanted the concavity up and the concavity down is really about, is f double prime positive or negative? Concavity is defined in terms of, was the tangent line getting steeper or shallower, or is it, concave up is really being above the tangent lines, whereas concave down is about being below the tangent lines. The tangent lines are getting more and more negative. That's a rate of change of f prime, which would be f double prime. So that's plus and minus there. So what we want to do is find when f double prime is positive or negative, and this is just like we're looking for f prime being positive or negative. The only time this function is going to be changing is when it hits 0 or it's undefined. This is never undefined. So what I need to figure out is when f double prime of x equals 0. Right, so that's going to be 6 minus 6x equals 0. Factor out of 6. So we're talking x equals 1 is the place where f double prime might change. It might be positive on the left and positive on the right. It's entirely possible. That happens occasionally. But in this case, it's not. And so what we can do is we'll, just like before for finding increasing and decreasing, except now we do it with f double prime. At 1, we know that to the left of 1 it'll be entirely one thing, positive or negative, and to the right of 1 it'll be entirely one thing. So f double prime of 0 seems like it's going to be easier to work with. 6 minus 6 times 0. We're really testing, do we want to know is the second derivative positive or negative? That's how you determine what to plug in. Students often have trouble. What do I substitute into? Well, do you want to know concavity, or do you want to know slope? Or do you want to know height? That should tell you what to plug into. I want to know concavity. That's positive. So that's going to be positive up there. And something bigger than 1, let's go with 1,000. Pick whatever number, as long as it's bigger than 1. 6 minus 6,000, I'm pretty sure that's negative. So that's negative. This is sometimes something you don't have to write it all out. You can just think of it just by using a big number, although your teacher will probably want you to write it out just for grading purposes. All right, this means that we're talking concave up from negative infinity to 1, and concave down from 1 to positive infinity. There's our concavity up and down. Part F asks for inflection points. Well, the only place inflection points happen is where concavity changes. So this goes from positive to negative. So the inflection points are going to be at 1, comma, we want the y value that goes with 1. That's going to be f of 1. The original f of 1. I want to know the height at 1. F of 1 is 3 times 1 squared minus 1 cubed. That's height of 2. Right, so it's at 1, comma 2. The last bit of this problem asks us to sketch a graph of this function. So let's do that next. And when I'm trying to graph a function, and I've done all these calculations for it, there's a strategy that I like to use to keep everything straight. I like to, across the bottom, rewrite my f prime graph. Across the bottom, I also like to write my f double prime, not graph, but number line, and mark all my important values to the same scale as this is up here. So f of 0, something happened that was interesting for 0, and at 2, something interesting was happening for f prime. It was also 0 there. And then it was positive between them, negative and negative on the outsides. For f double prime, the interesting thing happens. Oh, I didn't actually write that to scale now, did I? That's going to be scale 1, scale 2, it's 2.5, 3. This is why it's a bad idea to do this in pen. You want to try to do this in pencil when possible, but that doesn't show up on the video as well. F double prime was interesting at 1 because it was 0, and then it was positive to the left, negative to the right. Some people like to write a bunch of little positives, a bunch of little negatives. It's fine, keeps you straight. I'm just going to line this up as best I can. We also found out that f of 1 was 2. That was actually an inflection point. Earlier, in an earlier video, we found that f of 2 was 4, I believe. 2 is 4. F of 3 we found was 0. F of 0 we found was 0. F of negative 1 we found was 4. You don't need all of these points, but I already got them, so I might as well capitalize on that. And there's a negative 16 way down there from the very first video. Now I'm going to do this lightly in pen, just because, like I said, pencil doesn't show up. What I try to do is connect the dots, but respect the increasing and decreasing. And sometimes that's going to cause weird kinks in your graph, although that won't happen for polynomials. You'll get everything very nice for the polynomial. I try to get my increasing, decreasing down first. Connect the dots. And then I try to smooth it out by making things bend the way they're supposed to. So it's decreasing and concave up. It should look like the left half of a U. If it's increasing and concave up, it should look like the right half of a U. And so on. As we move to the right, it should switch to concave down now. So I bend it above the straight line and concave down, bend it there. And that's more or less what we want. And then you go through, erase all your light marks, and you draw it darker. I'm just going to do it with a blue marker. And be careful, I got very close to curving in on myself. Make sure you respect the vertical line test as you're graphing a function. It's got a little sloppy there. And then it depends on the exact phrasings of questions as far as what you need to mark, what you don't. Commonly, you want to be marking things like absolute extremes, 2, 4, 0, 0. Often you mark x-intercepts, 3, 0. Inflection points, they usually want you marking them if you're graphing this by hand. And that's really the key features of this. It's not perfectly right. You know, at 1.5, it looks like that's 3, whereas if I plugged in 1.5 into f, I probably wouldn't get exactly 3. In fact, I know I don't. But it's good enough. It shows the major features. It shows the landscape. That's why it's called a sketch, not a perfect drawing of it. That gives you the large-scale features. It's just really what you want to focus in on when you're looking at a graph. Where is it peaking? Where is it at a value? And all of that. One last comment I'd like to make about this. Keep in mind, this original function, this is for curve sketching. This original function was x squared times 3 minus x. And so you can do a does this make sense kind of a thing. If you look at the intercepts, if you've got a function written as this times that, it's going to look like those two pieces, at least at the times that those two pieces are close to 0. So x squared, when it's close to 0, looks like that. And 3 minus x is a big line that runs through 3 with a negative slope. And so what we see here is actually sort of a blending of the two. X squared near 0, 3 minus x near 3. Because when they become 0, they drag the whole function, snap it to the x-axis. And in between there, just purely based on that, I was expecting something that does a nice blend them together. Something like that. Which is not too far off as far as increasing, decreasing from my original function. It's hard to tell where the inflection points are going to happen from all this. But at least this feels like a combination of x squared and a 3 minus x. This is another thing that you can try. If you see the function written as this times that, as a times b, you may know off the top of your head what the a looks like and what the b looks like. And so at the places where that's close to 0, you should expect the same thing to happen. I'll give you one last example of that. If I've got a function, I'll call it g of x this time, which is cube root of x and 4 minus x. I know to a degree what this looks like, because I know that cube root of x Near 0 is going to look a lot like that. And near 4 minus x, is going to look something like that. And now it's a matter of blending them. I have a pretty good idea that this function is going to go up, have a vertical tangent line at 0, and come down toward it. And I don't know exactly where that peak happens. Maybe there's extra inflection points that I'm missing. But still, I have somewhat idea what that looks like, based purely on knowing what cube root of x looks like and what 4 minus x looks like. So that's a technique that doesn't often show up in textbooks, but is a valuable way of analyzing, does this graph look right? Thank you very much for watching. I hope to post more videos about this in the future.